What if I told you that despite all the hype about multicolor, multimaterial, and multi-tool 3D printing, we're only just scratching the surface of what's actually possible? After all, these days, it seems like a foregone conclusion that multi-tool, multi-nozzle, and multi-material printing are the way of the future. I mean, just in the last couple of years, we've seen more and more companies come out with a range of different solutions to take advantage of the myriad benefits that multiple nozzles or tools can offer. But up until now, most of these advantages have been relatively surface level ones. No pun intended. Things like material savings from not having to purge colors, or faster color swaps, or best case scenario, the ability to print with two totally different materials that have two totally different print temperatures and flow characteristics. And while that might not sound all that surface level to you, in this video, we're going to explore one of the more cutting-edge, experimental, and exciting possibilities unlocked by multi-tool and multi-nozzle printing. The ability to print different parts of your objects, not just with different colors or different materials, but with entirely different nozzle sizes as well. Why is this interesting, you ask? Well, for the last couple of months, I've been hard at work dreaming up and testing various practical and real-world applications for this technology. And in this video, I'm really excited to finally show you what worked, what didn't, and how this is poised to make 3D printing better, faster, and cheaper in the future. Let's get after it. First things first, let's talk about how this type of 3D printing is even possible, because as I mentioned before, this is still a very new thing, kind of on the bleeding edge of consumer 3D printing. And as always, if you don't care about the actual mechanics of which printers can and can't do this and how to actually get them to do it, then you can just use the chapters below to skip ahead to see the actual use cases and examples. Still here? Okay, good. First, let's talk about hardware. While there is an increasing number of printers on the market now with multiple nozzles, INDX systems, index systems, and even a growing crop of really amazing tool changer projects, including my own, that you can build, the majority of these solutions do not yet support having multiple nozzle sizes in the same print, besides the Prusa XL. And even there, they do give the disclaimer that this is still advanced functionality and very much experimental. By the way, full disclosure, Prusa did sponsor this video so that I could actually afford to spend the time doing this research and testing and experimentation, and they also sent me a 5-tool-headed Prusa XL to play with. I'm gonna send this video over to them for approval as a matter of courtesy and so that they can fact check me on some of the technical stuff, because it is changing very rapidly, but I will ask that they not exert any kind of editorial or creative control over the content itself. But for those of you watching, if this video convinces you that you want to pick up a Prusa printer or some of their filament, I'd really love it if you use the link in the description, because that will show sponsors like Prusa that it's worth it for them to continue funding these types of research and content-related videos. Anyways, that's just the hardware. Yes, you can build your own stealth changer and put different sized nozzles on it, but even if you do, you're still going to be a bit limited by the software. On the slicing side, this is still very much experimental, and it will require some manual tweaking, at least for now. Let's take Orca Slicer, for example, which is my personal favorite slicer of choice. While you can select different print heads for the walls, the solid infill, or the sparse infill, and you can assign a different nozzle size to each of the different print heads for your printer, you are limited by the fact that those nozzle sizes are not actually taken into consideration when slicing. In other words, while the first few applications that I am going to demonstrate in just a second are already possible in Orca Slicer, some of them are not yet. But switching over to the official slicer for the Prusa XL, and honestly, probably the best slicer out there for tool changers overall, Prusa Slicer, the situation is a little bit better, but again, as Prusa's help doc is very clear to state, I cannot emphasize this enough, especially as we get into some of the actual print quality and examples. This is still considered advanced and experimental, and the bugs still need to be working out. Here, once again, you will need to change the nozzle size for each of the extruders, but as I found out, that is not enough to actually change the line widths because they're still dictated by the settings under the Advanced tab. Fortunately, to accommodate this, Prusa does now have a checkbox to automatically calculate extrusion widths. If you don't check this, even if you change the actual nozzle width under their printer settings for each of the extruders, you are going to have extrusions come out the same width as all the rest of them. I actually didn't realize this until well into the production of this video after having done, honestly, a lot of experimental prints, but in the end, it worked out and I discovered another cool functionality of multiple nozzle sizes. So I guess it's all good. Anyways, the lesson here is clear. If you are going to play around with these experimental features, first, it is best to use Prusa Slicer for now. And second, you should change not only the nozzle width for each of the extruders, but also make sure to tick that automatic width calculation box so it actually, uses thicker or, spoiler alert, thinner extrusions for the actual line widths. Another pro tip here that I do want to share because this cost me quite a few hours before I realized it. You do also want to make sure that any part that you want to obey the different extruders that you set for different line types is set to print as the default filament or tool. And then you can change what the default is for walls if you want walls to be in that extruder. If you manually set the object to be another extruder, for example, you have different objects on the bed and you set each one to a different color and different extruder, then that entire object will be in that extruder, including the infill. Basically, the rules will then be ignored. It is a little bit confusing. I mean, what is the default extruder? But again, we are on the bleeding edge here. And just one last note, because I do want to make this an educational resource for people who want to experiment in my path, there are still some things that I haven't been able to figure out or which aren't fully functional just yet. For example, when you paint a certain part or area of a model, for some reason, the logic to only print infill with one extruder is automatically ignored for that specific part. And the infill is then printed in that area in the same color and same settings and same nozzle width. I don't know if that's a bug or it's just something that they haven't baked in yet or figured out how to account for, but yeah, take that into consideration. Okay, so that's all the technical stuff of how to actually set it up. Why don't we go ahead and load up some different size nozzles and actually test some practical applications, shall we? I've recently gone down the YouTube rabbit hole of videos of entrepreneurs in the developing world who are turning waste plastic into bricks or tires into playgrounds or coconut husks into coolers. And I freaking love this stuff. It is the type of innovation that just fills me with hope and optimism about the future, which is in short supply lately. So the inspiration for this particular application was the fact that I, like many of you, have a ton of filament waste, purge lines, poops, and failed 3D prints of all different colors. And yeah, I could easily mix in virgin black material or pigment, or even take a majority of black regrind and turn all of that into black filament, but that either requires virgin inputs or it bottlenecks my throughput because I'm limited by how much black material I get my hands on. And that got me thinking, isn't it a pity that we buy all this beautiful, perfect virgin filament for our 3D printers and then waste at least 40% of it on infill that nobody's ever going to see? So ladies and gentlemen, allow me to introduce you to Fillerment, my line of 100% recycled filament designed to be used as filler for your 3D prints. Fillerment is the sausage of 3D printer filaments. We throw in everything: silk PLA, matte PLA, black, white, pink, blue. As long as it's PLA, it goes in. Unsurprisingly, the end result isn't pretty, but it doesn't need to be. It just needs to act as filler. Oh, and by the way, you don't need to have your own recycling rig to use this idea. Right now, as we speak, many manufacturers, including Prusa, sell lower grade or recycled filament from their production process for less than their perfect stuff. And I want to openly encourage other filament manufacturers to take this idea and run with it. Instead of throwing away less than perfect filament or the color contaminated filament that comes out of the extrusion line when you change colors, sell it at a discount as Fillerment for those of us with multi-tool head printers or multi-nozzle printers. I won't even charge you guys a royalty. But there is just one problem with this idea. To allow this idea to scale and ideally to make it cheaper than new filament, Fillerment will need to take advantage of more lax production standards. That means less rigorous material sorting to get rid of, say, PLA plus hybrids. More importantly, if we're talking about recycling failed 3D prints collected from the community, as I do, it also means that there will be a lot of the types of contamination that inevitably come with recycling. Metal shavings, small bits of glue, dust flecks, and so on. In other words, while I have had some success printing my homemade Fillerment with a standard non-high flow 0.4 nozzle, for the best reliability and the least clogs, you really want to print it with a 0.6 millimeter nozzle or even higher, and you have to stay away from any of the CHT nozzles or high flow solutions due to clogging. Now, that doesn't mean that you actually need to extrude 0.6 millimeter line widths, though you can if you want. Believe it or not, you can still use the same line widths in your 0.4 millimeter profiles with a 0.6 millimeter nozzle. Or, as I accidentally found out when I neglected to check that checkbox that we talked about earlier, with a 0.8 millimeter nozzle. To test this out, I tried printing the inner and outer surfaces of this trash can with beautiful virgin Polymaker Panchroma matte PLA, one of my favorite filaments. But instead of wasting good material on the actual infill, I printed that part of the print with Fillerment on a 0.6 millimeter E3D diamondback nozzle, which didn't clog or get damaged if any metal shavings passed through it. And in addition to saving virgin filament, this has another added benefit. Matte PLA is notoriously weak, especially with regards to layer adhesion. I normally would not dare to print something with this thin of a wall with matte PLA, especially not with one single 0.4 millimeter perimeter on the inside and out. But because my Fillerment is made of a hodgepodge of different materials, including much stronger PLA plus blends, I gain a ton of strength from the actual infill. Not to mention, I get this very cool pattern that bleeds through the ultra thin 0.4 millimeter walls. I can even choose different surface patterns on the walls by changing what type of infill I use, which is pretty neat, right? Now, in all fairness, I did choose to print a prime tower in this case, which I think wasted like 140 grams of material because I figured, why not? I can just re-recycle that into more Fillerment. But you can also use another object as a wipe tower or eliminate it altogether with the Prusa XL, as long as your filament is properly dried and tuned. So this success and excitement really got me thinking. If I can use a bigger nozzle to print materials that normally clog due to contamination, I wonder if a bigger, higher flow nozzle would also allow me to print materials that clog due to the actual material properties themselves. For example, from my 3D printed shoes video, I have a couple rolls of TPE and TPU filaments that are honestly nothing short of impossible to print on normal printers. But I really wanted to use those two filaments to make iPad stands for my kids because unlike normal TPUs, they provide a ton of friction when pushed against smooth surfaces, which with any luck will keep my kids from pushing the iPad off the edge of the table when they're talking to grandma and grandpa on FaceTime. But try as I might, literally nothing worked. Even on the Nextruder, which typically does a great job printing your standard TPUs, I had no luck. Inevitably, after a few meters of filament extruded, it just wrapped around the extruder gear and went full BDSM on the extruder assembly. Trust me, I tried everything. Nothing worked with these two filaments. And then it hit me. What if the issue isn't just the flexibility of the material per se, but rather back pressure? So here's what I did. I swapped one tool head on the Prusa XL over to a 0.8 millimeter E3D Obsidian high flow nozzle which should give me dramatically improved flow. I loaded another tool head, which was on a standard 0.4mm nozzle with PETG, since PETG and TPU bond together pretty nicely. Then I sliced everything normally, partially because, once again, I had not yet figured out how to get the slicer to actually extrude 0.8mm lines on only one extruder, but also because I wanted the details to be sharp on these hexagons. And to my surprise, it actually freaking worked with both of those filaments. Now, ignore these print quality issues. I did have the filament get snagged a few times on something on the shelf. And as you can see on one of them, I still do need to slow down even more for the line width extrusions. But dude, this is crazy. From literally getting the print head jammed in the first minute of printing these materials to completely finishing an 8-hour plus print with virtually no issues. And all I had to do was swap to a bigger, higher flow nozzle. Genius. Almost as genius as the other thing I figured out while doing this. You see, solving the jamming issue with a higher flow 0.8 nozzle is all well and good, but it's all for naught if your filament is so floppy that you can't even get it loaded into the extruder. Like many modern printers, the Nextruder has a filament sensor built right into the tool head, but that means that the ultra floppy filament won't push through and trigger it. Then, a breakthrough. I grabbed the Sunlu filament joiner thingamabobber and I joined that flippy floppy 70A TPU to a piece of PETG, and boom, I was able to easily load the filament just like normal using the PETG as a kind of disposable needle and then purging it before I started the print. Now, I don't want to toot my own horn here, but how brilliant is that? I feel like that kind of advanced pro tip has at least earned me a subscription, maybe even a subscription and a like. But now let's keep testing some other ideas, ideally ones that actually leverage different line widths in the slicer. So the kind of classic application that people mention when you think of different nozzle sizes within the same print is to use a less detailed, bigger and higher flow nozzle for the infill to speed up that non-visible part of the print. And we are going to do that in just a minute. But I think we can make it even more interesting by taking this idea to its logical extreme from both ends. See, instead of combining a 0.8mm nozzle for infill and then your standard 0.4mm nozzle for perimeters, what if we used an even smaller nozzle on the outside to give us the most detailed prints possible without having to print the entire thing with an incredibly slow 0.25mm nozzle? Now, I'll be honest with you guys. Prior to this video, I had literally never used any nozzle smaller than 0.4mm, simply because the amount of time that it would take to print anything substantial with one of them instantly turned me off. I'm not, as they say, a patient man. But with multiple tool heads, we can, at least in theory, get the best of both worlds. We can lay down the majority of the print with a standard 0.4 or even a 0.6mm nozzle, depending on how detailed it needs to be. And then we can go back and add the details with a 0.25. After all, I've been pretty outspoken about the fact that 3D printed text is really ugly. So I went about doing some calculations to see just how much time this would save. I compared 0.2mm nozzles for the entire print, 0.4mm nozzles throughout the print, and 0.4mm base layers with 0.2mm details. And even on very small prints, like these super secret QR codes that you definitely shouldn't pause the video and scan, the differences were quite significant, especially when you account for the fact that you do need to add an additional perimeter with the 0.2mm nozzle to get the same thickness of the outer perimeter. And that's not even considering the time savings of a tool changer versus a filament multiplexer, which honestly is outside the scope of this video. What's more, those time savings become even more exaggerated if we put down the base layers with 0.6mm nozzles. Now, this may seem like a gimmick, but I know for a fact that there are tons of Etsy businesses out there that are absolutely killing it with medium-scale customized products. For example, Wi-Fi QR codes for the tables of restaurants or individualized dog tags for sports teams. You name it. For these folks, a high quality product that is actually legible is an absolute must, but every additional print hour it takes to fulfill an order is money they're losing. And just look what happens when you scale up those time savings to, say, a full plate of 29 QR codes. Now, imagine if you needed to print like 200 for an order. For these types of folks, mixing nozzle sizes could be the difference between needing an entire fleet of multiplexer printers running 0.2mm nozzles versus needing 1 or 2 tool changers with 0.6 and 0.2s to complete entire batches of orders. But all of this is well and good in theory. What really matters at the end of the day is the end result. Does a 0.25mm nozzle actually yield better looking prints in these types of scenarios? Or is Arachne line generation so good these days that it doesn't really matter? Well, let's switch to future Jonathan and have a look. All right, we're back. I'm a few days older and a whole lot wiser. Basically, things did not go as expected, but I did some digging, I did a whole bunch of investigating and experimenting, and I think I figured it out. First, let me show you guys what was going wrong, and as I'm talking, see if you can figure out what the issue was. So on this side, you can see a QR code that was printed with 2 0.4mm nozzles, the same type that you would use if you used a standard multiplexer which changed filament but used one nozzle. And over here, you can see the combination of a 0.4mm nozzle for the base and a 0.25 for just the details. I'll also put up the times it took to print each of these in case you forgot. And as you can see, I had a major issue with the 0.25mm nozzle and getting the actual layers to adhere to the base. For another example, before I figured out what the issue was, I tried printing out some Gridfinity bins with printed text labels. Now, to make the effect more pronounced, I embossed the text up since the resolution will only be as good as the largest nozzle size on that layer. Now here you can see one that uses the kind of standard 0.4mm nozzle throughout. And here you can see 2 different samples that I did with a 0.25mm nozzle. And I did manage to get the text to adhere to the actual base of the print, but the quality is no better than a 0.4mm nozzle. In fact, I think it's actually much worse, and there are some holes and gaps inside the text. Now, it took some real noodling and some real experimentation here, but eventually I figured out what the problem was, and it's a really, really educational moment for all of you who want to experiment with this. So, as you may or may not know, every 3D printing nozzle size has a minimum and a maximum possible layer height. Now, generally, the maximum is about 75 to 80% of the nozzle diameter. So, for example, you can really only print up to a 0.3mm height with a 0.4mm nozzle, because anything beyond that and you're not extruding enough plastic for the bead to actually stick to the previous layer. You're limited by the kind of flow. Now, I'll spare you the gory details of exactly what I did wrong, but basically I was using too large of layer heights because I was allowing the bigger nozzle size and profiles to dictate the layer heights, which was obviously too big for the smaller nozzle when you have such a wide variance. But like, how do we actually solve this? I mean, you can't actually print like 0.1mm layer heights on a 0.8mm nozzle. And even if you could, you would really negate all the time savings of using that bigger nozzle. So here's what I did, and try and stay with me, it's a little confusing. First, and this is an important one that I should have paid much more attention to on Prusa's web guide, I went in and I also added the profiles for the 0.25mm nozzle for the Prusa XL. Then I made sure to select those profiles, the profiles of the smaller nozzle that I wanted to use for the entire print. That's important, so I'm going to repeat it. For my admittedly limited testing, you want to select the profiles for this smaller nozzle, for example, the 0.1 speed profile that's only available for the 0.25mm nozzle printer preset for the base. I actually thought that I'd selected the profiles for that one, but when I went back and looked in editing, I realized that I had selected the 0.1mm speed profile, which is actually from the 0.4mm nozzle printer config. Still, I think it is important to select a small layer height or possibly a layer height which is in the range of both nozzles, not say 0.2 millimeter, which is out of range for the smaller nozzle and which caused the issues I was having before. More testing is needed though. Then, and I think this is particularly clever, I used the variable layer height feature to calculate the ideal layer heights, sliding it around and experimenting with different levels of quality versus speed until I got my ideal height for the base layers, which were going to be printed in the 0.8 millimeter nozzle, and I got those set to 0.3 millimeter layer heights. And for the rest of them, I got a variation from 0.1 to 0.07. I know, it's confusing, but basically I forced the printer to do different layer heights at different parts of the print. Now, a side note here, you cannot have different variable layer heights for different objects if you want to use a wipe tower. So if you do want to print different objects or even the same object multiple times, then you will need to merge all the different objects on the build plate into one and then use the same variable layer height map for all the different objects. Okay, but wait, what about switching the tools or the colors? Well, on the face of it, there are two ways to do this, but only one of them works. Now, you might think that the fastest and easiest way to do this would be a tool change in the slice preview above a certain height. However, as I learned, that won't work because it won't apply that automatic extrusion width checkbox, since all it's doing is taking the G-code that it already sliced and switching which tool actually executes it. So the end result is that you will get thicker extrusions, which are based on the thickest nozzle, but you'll use a tool head that isn't compatible with them. So instead, what you need to do is take your merged object and then use the painting feature, but paint by layer height. Then, and only then, is the slicer going to properly calculate both the correct layer heights for each extruder, as well as the correct line widths. Now, it's easy to get this wrong. Like I said, it's super confusing. If you miss any one step, the automatic extrusion width checkbox, changing the nozzle width for each extruder, the adaptive layer heights, or painting with the correct extruder for each area, it's not going to be sliced correctly. So I highly recommend that you go over to the sliced preview and you check both with the layer height option selected as well as with the line width option selected to make sure everything is copacetic before then triple checking with the tool option selected, and then, only then, do you hit print. Now, the end result is honestly pretty astounding. It is so much better than it was before. Obviously, this QR code, which is a totally different one that you definitely should not pause the video and scan, it's not that detailed, and I'm sure that you can do much more impressive stuff than this, but it does show just what's possible with this little trick. Now, here's the example that you saw in the slicer preview. Now that I have it working properly, I'm ready to stretch my legs and try something a little more advanced. It is a segment of a larger relief. The base is printed with a 0.8 millimeter high flow nozzle and 0.3 millimeter layer heights, but the elevation details are printed with the 0.25 millimeter nozzle with variable layer heights between 0.1 and 0.07. And just look at the detail. And I obviously did make the base part of it very, very thin to save on time and filament just for this proof of concept. Again, I think you definitely should enable the ironing feature to get that top layer to be much cleaner, or just add another top layer, because maybe I didn't have enough top layers here, but I actually calculated how long the full-size reliefs would take at the various different options, assuming you're going to use two different colors either way, and the differences were quite staggering. And here, unlike with some of the other examples I'm going to show you, I really do think that the capability of the 0.25 millimeter nozzle with the level of detail that it's able to provide really does yield a significantly nicer end product. But you could also imagine doing a hue forge with this, especially if you want to have a nice and thick base. You would just lay down a thick 5 or even 10 millimeter base and then let hue forge do its magic with those ultra thin layers, and do those with an ultra tiny 0.25 millimeter nozzle. I am going to try and find some time to experiment with this after recording. I have not yet gone down the Hue Forge rabbit hole, and I don't want to delay this video any more than I already have. But let's see if we can take this one step further, because while having intricate detail on one layer, the top or even the top and the bottom, is cool and all, a 0.25 millimeter nozzle is capable of much more. So what if we were to print our infill with a 0.8 millimeter nozzle running, say, scraps of filament that we want to use up, but then for the perimeters, we used a 0.25 millimeter nozzle to try and get as much detail out of the print as possible. Of course, this will mean that we will need to do an extra perimeter around if we want comparable strength. And the flow rate on a 0.25 millimeter nozzle is understandably quite low, but maybe, just maybe, it'll be worth the added time. To test this out, I loaded one of my favorite models from Eastman, this Deadpool bust, because it has a level of detail that is really suited for resin 3D printing. I also loaded up the 0.5 millimeter structural profile on the Prusa XL and modified it to use 3 perimeters instead of 2. I chose 10% gyroid infill, but because of the small layer heights and the massive high flow 0.8 millimeter nozzle that we're using for infill, I allowed Prusa Slicer to automatically calculate the optimal combination for infill layers with a max of 400%, which should help us take advantage of that nozzle and turn it into some real-time savings. As sliced, the 0.25 and 0.8 combined print comes out at just under 12 hours. For comparison, using a 0.4 nozzle with a 0.8 millimeter for infill gives us about 10 hours. But perhaps a better comparison would be your kind of standard no frills print. In other words, using a single 0.4 millimeter nozzle for both inside and out with no nozzle or tool changes, 2 perimeters, and 100% maximum infill layer combination. And that very common scenario brings us in at 6.5 hours, just over half the time of our 0.25 and 0.8 millimeter combination. But is it also half the quality and detail? To find out, I printed both, and here's future Jonathan to share with you the results. And I'm back. But here, once again, things didn't quite go as planned, at least not at first. So here, I think it is, you can see the standard 0.4 millimeter nozzle version, all printed with 0.15 millimeter layer heights, but with the same nozzle and tool for the entire print. And here is my first attempt at a 0.8 millimeter nozzle for the infill with multiple perimeters of 0.25 for the outer perimeter. Obviously, this didn't go so well, and you can see here that there is a bunch of bleed, but I did realize later that this was due both to the inner filament not being properly dried and probably me using a profile that wasn't perfectly tuned for the inner matte PLA. Just to be certain, I did go back and I tried the experiment again, but this time I used a 0.4 millimeter nozzle on the outside perimeters with the same 0.8 on the inside, but I used Prusament PLA and Prusament PLA profiles both inside and out. And you can see that except for one small area with bleed, it turned out just fine. With that said, if you compare the 0.25 millimeter outer shell version with either of the 0.4 outer shell versions, you honestly don't see any more detail with the 0.25 millimeter one. This is either because the details on this particular model are too small for even a 0.25 nozzle, or because Arachne line generation has made 0.4 millimeter nozzles just as capable of producing just as much detail. Now, I do think that there are probably a lot of middle ground models out there with medium-sized details that will show up a lot better on a 0.25 millimeter nozzle than they would on the 0.4. Though here, once again, I'm going to try and spend a little bit more time experimenting with this after recording this, and hopefully I'll be showing some of my results in some upcoming YouTube shorts. So do make sure that you're subscribed if you want to see all of those. All right, this video is getting really long and I should probably wrap it up. I do, however, have a couple of other ideas that I think could potentially be very interesting, but which didn't make it into this video. First, I think it could be really, really cool to experiment with using 0.25 millimeter line widths for supports to reduce both filament waste and surface artifacts on prints where supports are necessary. Second, I think it would be very interesting to see if we can combine expensive carbon fiber filaments for the outer shells with lower cost filaments like PLA or even plain nylon for the infill. I know that Stefan from CNC Kitchen has done some experiments that have shown that infill is much less important than perimeters when it comes to actual part strength, but I do wonder if that also applies when we're talking about both parts and materials that need to be able to withstand high heat. And finally, with all of that, I want to turn it over to all of you. What are some uses and applications that you can dream up to take advantage of this experimental new capability? Both myself and the folks over at Prusa want this video to serve as a kind of primer, a way to raise awareness about this new capability. But as always, we're looking to the collective creativity of the 3D printing community to figure out the actual best possible uses for it. So I hope to see all of you down in the comments, where I'm sure there will be some real gems that I haven't thought of. That's all for this week, but I'll see all of you on the next layer.